Hi, and welcome to Programmatic HSI with Python, where we'll be discussing the new TekHSI and TM data types Python libraries. In this video, we will cover our new Python libraries, TekHSI and TM data types, how to install the new TekHSI Python libraries, some programming examples, including using TekHSI and TM data types to plot waveform data, as well as create and read waveforms programmatically. And finally, we will discuss how the new Python libraries compare to using traditional CurveStream methods. HSI is a Python library that provides a low-latency, high-speed data link between Tektronix scopes and a host computer using Google's Remote Procedure Call Protocol, or gRPC. This library is designed to provide a reliable and efficient way to transfer data between devices, especially when dealing with large amounts of data. TM data types is a Python library to help translate between the scope's binary waveform objects into the more popular waveform formats like .wfrm, .csv, etc. TM data types Python library also provides Pythonic data types for standard test and measurement waveform types like analog, IQ, and digital signals. Installing TekHSI will automatically install TM data types, so there's no need to install both libraries separately. As mentioned previously, installing the Python libraries for TekHSI and TM data types is as easy as simply opening your command prompt and typing pip install TekHSI. This will install both libraries and all of the requirements. In this example, we are importing the TekHSI and TM data types Python libraries along with the matplotlib Python library in order to use HSI to generate a very simple plot. So as you can see, the first thing we're doing is using HSI to connect to the oscilloscope. And upon that connection, we're going to access the data and store that data as analog waveforms. Now, as mentioned previously, HSI is pulling back binary data, which is why it's so fast. And so we need to use TM data types in order to format it into something that's readable by matplotlib. So we define our plots, and then down here, we check that there's data on our channel 1 and channel 2 on our scope, and plot the normalized X and Y axis values. Pretty easy. So all we're going to do is hit run. And just like that, we have a graph of what's going on my scope right here in Python. So in this example, we're using math to generate a sine wave, and then using the TM data types Python library to convert that raw data into a .wfm file, which is actually readable by an oscilloscope. So as you can see here, I have my parameters all initialized, including my record length, my frequency, my amplitude, etc. And here I'm using the analog waveform function to kind of just initialize this waveform variable where I'm going to be storing all of the characteristics of my sine wave, including the name, my x-axis, axis spacing, the offsets, all that good stuff. Now, down here is where we have some options in creating our sine wave. Really, you can use any math you want. This first example is just a very simple for loop where in the range of the record length that we want our sine wave to be, we're generating our sine wave points and putting them in the points array, which is then dumped into our y-axis values to be converted by TM data types. The other method, this one's a little bit more compressed. As you can see, it's only one line. We're just using an array immediately with NumPy to put everything that was going on in this for loop in one nice single line of code. And then kind of the faster approach, at least from a computer processing angle, is using vectors, again with the NumPy Python library. And as you can see here, we're using the linspace function and just in 2 steps doing some math and coming up with a waveform. And once we've generated our sine wave with whatever math and formulas that we choose, we're then going to use a try statement where we write that data that's been converted by TM data types using the write file function into a waveform that's readable by a scope. And then I just have this little debug statement to let me know in the terminal whether the file writing process was successful. So let's hit run. And it looks like we've successfully created a sine wave waveform. So then it's like, well, what am I going to do with this test waveform? Well, I also have an example here on how to read waveforms, whether they be from the oscilloscope or generated using Python code. Once again, we're only using TM data types, and then we're going to plot it with matplotlib. So here I have a statement where basically we're checking for what is the file's format. Is it an analog waveform, an IQ waveform, a digital waveform? And it's going to use TM data types to convert any of those formats into something more normalized and readable by matplotlib. And then from here, we're setting up our plot and showing it off. So if I press run, I drag my plot over, you can see a graph of that sine wave that we generated in the previous script. Now this last Python example is using CurveStream to pull data from the scope. And we're showing this to kind of highlight the comparison of operating a scope using HSI versus traditional Skippy and CurveStream command methods. So off the top, we can see that the CurveStream example is a lot less readable than the prior HSI examples. And this is partially because we need to use Visa wrapper in order to communicate with the scope. So there's all these extra scope.write commands, and then our Skippy commands are these strings. And unless you're really fluent or know your scope very well, it might not be immediately obvious what these commands are doing. Also, unlike HSI, we have to do all of the formatting, the turning the scope on and off, pulling the data. That all happens manually. And whereas HSI will pull as much data as possible until you have a complete waveform as quickly as possible, CurveStream, what we're doing here is we're setting the operation limits. So all you get is as much data as you can within a 10-second period, at least for this particular piece of code. And so if I run it, you can see that it runs within the constraints that I've given it, and it runs much slower than the HSI example. Some key takeaways to understand about the new Python libraries are that TekHSI and TM data types support the MSO4B along with all variants of MSO5 and 6 series oscilloscopes. that the new Python libraries can easily integrate into your existing Python automation environment. These new libraries work extremely well with the TM Devices Python library and can completely change how you write code for your instruments. And finally, and to some of you, most importantly, HSI and the new Python libraries are completely free. Thanks for watching. Be sure to visit tek.com to download and install the new TekHSI Python libraries today.